Okay, sir, this is the third video for explanation the code that we use the PSO case for MATPOWER, as we mentioned in the two previous code. It should be the first thing it is to install the MATPOWER, and after that the code it will be run. Today is after we finished from explain the base case. Today we will go to through the PSO particle swarm theorem case to explain how to work, and maybe in the next video we will explain the result. But before that result, now we start to explain the code. As you see here, the first file, it is the profile. In the profile, we have a profile for 24 hours for IEEE 33 buses system in per units. We have three type of profile. The first thing, it is the load profile. The second, it is the PV photovoltaic profile during the 24 hours, and the last column, it is for the profile for battery storage, as you see here. In the profile of the battery storage, we have positive value and negative values, but the positive value, it is mean that as charging the battery, and the negative value, it is mean that discharging the battery. This is the first file, and the second file, it is the PSO case. It is the main case program. From here we can run the program. As you see here, clear all the variables and CLC the command window, and after that go to the PSO function that will be explained later, and after we get the best solution from the optimization, apply this best solution on the result function to get the result. As you see here, to get the size of PV and the size of battery storage and the size of the location for the PV and battery storage, and then also the power flow result, the power losses and voltage deviations. This is the main program. If you go to the optimization PSO file. Now the PSO, it is implementation of the particle swarm optimization MATLAB. The first thing, it is to problem definition. As you see here, the number of variables, decision variables, the number of decision variable threes, it is the size of PV, the size of the battery storage, and the location of the PV and battery storage. As you see here, we have the lower band parameter, the range of optimization for the three variables, the lower and the upper. And as you see here, the PV size from 0 to 6 kilowatt, and the same thing for battery, and the location from 2 to the 33 bus. And after optimize that, after problem definition, now PSO parameters as maximum iteration, the population size, the inertial PSO parameters, the inertia weight, damping ratio, the personal learning coefficient, the global learning, and the velocity limits. It should be between the minus value of the maximum velocity and the 0.1, between the difference between the maximum and minimum value of the variables. And after that, initialization started. As you see here, started with empty particle position and particle cost, velocity, best cost, and best position and best cost particle. And then we also define the global best. And the first step, as you see here, it is the initialization process before we go to the main loop. As you see here, initialize the position, the particle for each position. Each particles contain, as we defined before, it is contain the size of PV, the size of PS battery storage, and the location of the battery and photovoltaic. It is in the initialize the position process. It is the first thing in the initialization process. We define the particle randomly, and after that we defined or initialize and assume the velocity of each particle, it is 0, and then we evaluated the cost function that we will explain later. And after we calculated the cost function from each particles, we get the particle cost stored in the particle cost, and after that updated personal best, because we don't have any other historical cost for each particle. Now we consider the cost that we get it from the initialization process as a best position and best cost, and then we will update the global best. The global best, it is mean that the compare between all the particles that we existed here, and get it the best one, the particle that gets the fitness function, it is lowest compared with other particles, and it is repeated this process for all the number of particles, and then also we initialize the best cost, it is 0 for the maximum iteration. After we finish the initialization process, and now we go to the next step for the PSO main loop. We started with the iteration from 1 to the maximum iteration that we defined before, and after that, depending on the initialization process, now we will update the velocity. As you see here, the velocity of each particle, it is dependent on the initial velocity, and also the particle, the best position of the particle, and the current particle position, multiplied by the random and some factors, and also some with which is the global best, and the difference between the global best position and the current position of the particles. And after that, we calculated the velocity for each particles, and after we calculated the velocity, we applied the velocity limits, and then we updated the current position. The current position is dependent on the new position, sorry. It is dependent on the current position, sum of the velocity of each particles. So after we updated the position, we applied the position limit. We see if the new particle position is in the range of the minimum and maximum values that we considered or not, and after that we applied this limit on the particle and get the new position. And after we get the new particle position, now we go to the cost function to calculate it, or evaluation the particle cost, the new particle cost. The new particle cost of the new position, now we compared with the best that we stored from the initialization. If the cost of particles now it is less than the best cost that we get it in the initialization, now updated the particle position, the best particle position, and the best cost particles, as you see here. If not, we go also to update the global. We compared with the global best. If the new particle get the lowest value compared with the global best, now we updated the global best value and repeated the process for the first for the number of population or particles, and then we printed the best value that we get it from the first iteration on the screen, as you show here. So after that, we repeated this process for the number of iteration, and in the second iteration, now we have the initial velocity from the first iteration, and we have the best and the current one, the new current one, and the global one, new global position if you updated, and the particle position, and then we calculated the velocity, the new velocity, new particle position, depending on the new current position that we get it from the first iteration, and the new velocities that we calculated before, and then we get the another new position particles, and then applied the position limits and evaluation the cost function, and updated the personal best, and updated the global best, and repeated this process, and then also printed the best value on the command window and repeated this for the maximum iteration. After we get the best position, the best solution from the global best, as we mentioned, the best solution contain the installed capacity of PV, installed capacity of battery storage, and the location of that battery and PV, and then we printed the best function or best cost, how the fitness function behave with the iteration in the graph. This is the process. Now, after we finish the PSO, as you mentioned before, we go to the result function, get it the best solution, and put it in the result function to get it the result. The result function, it is for the same thing of the cost function that we will explain in the next video. We hope it is clear for you. If you have any question, we are ready to answer you, and we can help. We will help you as much as possible. Thank you for your listening, and see you next video.